Good afternoon, everyone, and welcome to the second day of 1 week international FDP conducted by Department of Mathematics, PRDS College of Arts and Science on the topic Real, Applied, and Computational Mathematics. Some general instructions for the candidates. Attendance is mandatory for all the days. Feedback form link is already posted on the YouTube description box, but it will be activated only at the end of the section. Now, I would like to invite Dr. Jayanti LS, HOD, Department of Mathematics, to deliver a welcome speech.
Good evening, everyone. I am here for welcoming Dr. Pang Kang. He is an associate professor at the Department of Mathematics and Statistics, Faculty of Applied Science and Technology, University Tun Hussein on Malaysia. I have any immense pleasure to welcome you for the second day of International Faculty Development Program, sir. Actually, he serves as Head of Center of Research for Computational Mathematics, University Tun Hussein on Malaysia. He received the PhD degree in Mathematics and Statistics from Curtin University, Australia. His research interests including in areas of fractional calculus, specifically in numerical analysis for solving fractional differential equation. Currently, he has 3 PhD students and 4 already he graduated. It's our immense pleasure to be here. Thank you, sir, for making your time for us. Over to you, sir.
Yeah, thank you. Thank you for the mathematics department, PRDS, for giving me this opportunity to talk on my research interest. So, which I give the topic fractional calculus, and then numerical and applications. Ladies and gentlemen, so hopefully you can see my slide. So my name is Pang Chang. So I'm from Center of Research in Computational Mathematics, Department of Mathematics and Statistics, Faculty of Applied Math Science and Technology, University Tun Hussein of Malaysia. Today, so I divided my talk into three main parts. So the first part I will talk about introduction and definition of fractional derivative, which is included various some definition for fractional derivative and integral. And secondly, so I will talk about one of the numerical method. So based on the orthogonal polynomial and wavelet, which is operation metric uh, for solving the fractional calculus problems. And then for the third part of my presentation today, so I will talk regarding some of my recent work, so regarding these fractional logistic equations, so which is I can consider that this is one of the application for fractional calculus. To be more specifically, so I will talk that how we use modified Euclidean number so as the solution to fractional logistic equations. Ladies and gentlemen, before I continue, so please allow me to introduce my campus or my university, because I think mostly from India, you are not familiar, or maybe you never heard about my university. So my university is a small university, so which is we have around compared to some other existing university in Malaysia. So we have two different campus. So what you see here is our campus. So it's my campus in Pago, in campus Pago. So you will see here all this building is teaching factory and the lab. So this is our main building, and our department is located in this campus. So where are we? So we are near Singapore, so which is about a 2 hour drive from Singapore and also about 2 hour driving from Kuala Lumpur. Before I further continue, because this year, so in December, early December, we will organize a conference, international conference. So because due to the condition for this COVID-19, so we have no choice to do the conference on the virtual conference, online conference basis. We hope that can get some research paper or some of your colleagues will join this conference. So we will publish our conference proceeding in AIP proceeding. Yes, ladies and gentlemen. So this is my research interest. So I interest in mostly for computation method or mostly for the numerical solution for various fractional calculus problem. So apart from that, so I also study the dynamical system, so which is related to mathematical biology. So this is the current research grant that I have provided by the Ministry of Higher Education Malaysia. And this is some of my recent publications. So just we have only few in European Physical Journal Plus, and then also from Mediterranean Journal of Mathematics, and then also from Wiley Mathematical Method in Applied Science, and also from Applied Numerical Mathematics Elsevier. Ladies and gentlemen, I think perhaps that so some of you or maybe many of you already heard about this fractional calculus. So if we go back to see the history, so this we can say that the first time so that fractional calculus appeared so in the mathematical society or the in the community is the later. It's a combination between Leibniz and Young L'Hopital. And then so there are questions. So if we have the derivative instead of the order n, which is integer, so if there are the order changed to fractional, such as 1/2, so what will be happening? So the Leibniz answer that it will be lead to the paradox. So from which one day useful consequence will be drawn. So this is happening few hundred years ago. People at that time may not really know. So the applications or even maybe not able to explain in more detail regarding this fractional derivative. This is the a book that introduced my master student, and then I think this is a very famous Indian mathematician. So he wrote the book regarding this fractional calculus. I think the title itself, and then also the content is very interesting, and which is the kindergarten of fractional calculus. So perhaps if you want to know better regarding fractional calculus, I think this is a book that I highly recommend to you. Ladies and gentlemen, fractional calculus actually is the generalizations of ordinary differential equations and integrations to an arbitrary order. So rather than we talk about fractional, we can talk about an arbitrary order. So because maybe you can have a 0.95, okay? What proved to be valuable tools in the modeling of many phenomena in the field of physics, chemistry, engineering, aerodynamics, electrodynamics of complex material, and then also the polymerology. And then for the modeling and simulation of the system and the process, so based on the description of their property in terms of fractional derivative, so we lead to the differential equation of fractional order, so which is we call the FTE. And then because of this FTE, so it is necessity for solving such equations. And then, however, so there are considerable many methods able to solve the fractional differentiation equations. which is including the Edomian decompositions, variational iteration method, homotopy perturbation method, and also the predictor corrector method. So you can see that so all these numerical method is very successfully to solve the integer order differential equations. And then mathematicians are extend it with some modifications to solve the fractional differential equation problems. And then another method that I think is around more than 10 years, around 10 years. So people are starting using the orthogonal polynomial, okay, uh, to use orthogonal polynomial to write the solutions or to find the solution of fractional differential equations. So basically, this orthogonal polynomial actually is not only orthogonal polynomial, so even the semi-orthogonal polynomial or maybe the non-orthogonal polynomial also applicable for this purpose. So basically, this kind of polynomial method is reducing the fractional differential equations to a system of algebra equations. And then from solving the system of algebra equations by using some other numerical method, then hence we can get the solution for fractional differential equations. So the polynomial that frequently being used might be including the Legendrian polynomial, or maybe the shifted version, the shifted Legendrian polynomial, Chebyshev polynomial, or shifted Chebyshev polynomial. So via some other things like spectral tau method or by using the collocation scheme. So let me give some example. So regarding how we do the fractional derivative. So this is the I'm using the mapper. So mapper have the built-in command. So which is the fracdiff. Um, so we take this as functions we want to differentiate. Say for example x squared, and then we say we want to differentiate with respect to x. So this is x. Okay, so then this 0.5 here is the order of fractional order that we want to differentiate. Excuse me. So 0.5, so basically you will get a coefficient here, and then you will see that the power x squared, so it be reducing 0.5. I think it's common sense for this 3 over 2 here. So say for example, if we want to differentiate x squared with respect to x for order 1, which is the first derivative. So our power will be reducing 2 minus it will be reducing from 2 to 1 because if we have the first derivative, right? So now if we have the half derivative, the same thing. So the power will be reducing, will be subtract 0.5. 2 minus 0.5 will be get 3 over 2. So another simple example. So we have this x squared. We want to differentiate with respect to x. And then for 0.9, okay, so what the answer? So we will get some coefficient here. So later I will talk to you perhaps that how to get these coefficients. Okay, and then the x squared, so power 2. So reduce 0.9, we will get 1.1, which is 11 over 10. So here we get the x power 11 over 10. So how does the thing look like? So after we do the fractional derivative. So this is I try to plot that 2x. 2x is the first derivative. So this is 2x. This is 2x. We get this one. So 2x, a straight line, right? So straight lines. So after we do the first derivative for the function x squared, and then if we do the fractional derivative for 0.9, the order is 0.9, you will see that is very close to when we do the first derivative, the ring color. If we have this but it's still very close to first derivative. So that's the nature of fractional derivative. So how we get this answer for a fractional derivative? So basically, one is extended to variable order. So what is the meaning of the variable order? So the fractional order, so we say that is 1/2, 3/4. So variable order is when we do the fractional derivative with respect to 2t. Okay, so all the t squared. So the order is not only 1, 2, 3 or 1/2, but the order is becomes a functions in terms of t. And then we have some other definition like Caputo Hadaman, like Macau, and then starting from 2015, so there are another definition coming out, so which is so-called the Caputo Fabrizio, so which is the non-singular kernel, and then also for the Ataga Polynomial, which is using the mid-tag functions and Pravaka and so on. But this new fractional derivative is controversial. So which people, many people, many mathematicians start to realize that this cannot be considered as the fractional operator, a fractional derivative. So we have to be very careful when we want to use this Caputo Fabrizio or Artagnan polynomial. So for the maybe you would like to explore more regarding this fractional calculus. To be honest, I just in the also in the I'm still very young, very new in this fractional calculus. So we compare to all those very well-known scholars. So I will suggest that. So if you want to know more regarding the definitions for the fractional derivative and the fractional integral. So I think this is a very good paper. So and that you might refer. And then also talking about the research opportunity. So in this field, I think many different field are able to do some things for in this research area. So if you are from the pure mathematics, maybe you can interest about the existence and uniqueness of some fractional differential equations. So if you are in the computational part, so might be we can have the numerator, we can study the numerator analytical solution or semi-analytical solution for various fractional differential equation problems. So if you are from operation research field, might be you can interested about the optimal contour. So if you know stochastic, then you may have to study this fractional stochastic differential equation. Then if you are in the applied maths, so might be modeling and many applications. And if you are in the chemistry, physics, engineering, so might be also a lot of applications that we can explore. And also, particularly if we are in computational mathematics, so there are a lot of methods that we can explore. So like integral transform, the Laplace, Fourier, Marine. So this is some of the very famous tools that be using in this fractional calculus problems. And then also for finite difference, finite element, Galerkin, and then also for this polynomial and wavelet related method. And if you are in applied mathematics, might be so we are interested about to study the stability and bifurcation analysis for fractional model. So, ladies and gentlemen, so let me introduce to you that one of the very famous definitions derivative. So this derivative, so basically it's like that. So we take the functions. Say for example, just now we have the x squared. Okay, so then we change the variable of the functions to tau, say for example, and then we multiply with a function. So we a t or minus tau, the alpha minus 1. So this alpha is, if this alpha is integer, so if we go back to the integer derivative or integer integrations. So if this alpha is fractional, so then we solve these integrations. So we do the integration with respect to tau, and then we integrate from 0 to x. Okay? And then to normalize condition here, we have the gamma alpha. So this is the Riemann-Roederer fractional integral operator. So if we want to do the derivative, so what we are going to do is we take the integrations, then we differentiate it. And this is the basic things regarding the Riemann-Roederer fractional derivative. So another version, so which is the most common being used in practical problem, is the capital fractional derivative. So difference than the Riemann-Roederer, the capital derivative here. So we do the differentiation first. Then we do the differentiations. So for, this, if we have the alpha, so alpha, say for example, we want to do the fractional derivative for 2.5 order. So then when we take the n here is bigger, n which is n is in integer, then n is bigger than alpha. So alpha is 2.5, then we take n is 3. So that means that we take the functions, provided the function can be differentiated 3 times, then we take the fractional we take the derivative for third derivative, and then we multiply with this terminal here, x minus tau, alpha minus n plus 1, and then we take the integrations, and then normalizing condition. Okay, so for this capital fractional derivative, of course, if we want to differentiate for the constant, okay, for the constant, so for the any alpha order, then we straight away to say that this should be, we get 0. So normally we are interested about when you have the x power something, x power beta. So say for example x power beta. So how's the answer look like? So if we have the x power beta here, say for example beta here is 0.5, alpha is 2, then we will get x is 2 minus 0.5, which is 1.5. Okay, then the coefficients, how we get this coefficient? Remember that I taught to you previously. So this coefficient, how we get this coefficient? If this is the only x power beta, then we can easily get the coefficients, the value there. So which is given by this the gamma beta plus 1, then over gamma beta plus 1 minus alpha. So I put into the mapper, then you can easily get that this is the capital. I just define my own functions. So this is the capital derivative, which is you have the alpha, I define it alpha n f, and then I write down this is the differentiate until n time. So say for example, just now is alpha is 0.5, so we just take the first derivative, n is 1 if not. If we have the alpha is 2.5, then you can take this n to 3, okay, third derivative, and then just put the value. So for simplicity, I'm not using tau here, I'm just using r because it's easy for me to type. So putting into here, so I just try to test it. So when the r is the function is in terms of x squared or r squared, so then we take the all fractional derivative order 1/2. So if we have this is 1/2, the ceiling function is 1, right? So I mean the integer which is slightly bigger than this alpha is 1. So according to this, then we get this. So that means you put this r squared into here, differentiate it, and over this x minus r, so 1/2 minus 1 plus 1, then integrate it from 0 to x. So we will get this one. Right? So this is equivalent with the built-in functions by using the built-in functions in mapper, which is frac dir. Then people are starting to extend this Riemann-Roederer or capital fractional derivative of the fractional order to more general terms, which is in the variable order. So how does the thing look like? So basically, so I mean for this order, so instead of fractional, so they extend it to variable order. It is happening, or it is possible here. So what we do is just substitute the alpha, which is previously is the fractional order, so to some function here, and then basically other definition is the same thing. So the only thing, the alpha here is more general, not only the alpha, but in terms of function t. So the same thing for the Caputo. So the Caputo, so also there are many researches regarding, so to extend it to variable order Caputo fractional derivative. So which is we have this one. Okay, so the previously we have the alpha here, then we extend it to so n minus alpha. We have the different definition for left Caputo fractional derivative and right Caputo fractional derivative, but the more common one is the left fractional derivative. So there are various definitions for this fractional derivative. So another one is Caputo Hadaman. So I'm using this slide here to compare that. So this is the Caputo, this is the Caputo fractional derivative, and this is the Caputo Hadaman. So you will see that. So what we are going to do here is we have a difference term. So like this Caputo Hadaman fractional derivative. So we have this multiply with this term. So another fractional derivative, which is we call the Markov, so which is not very famous, but actually have a long history here. So I mean to do, I think is you can refer to the books for the sample. And then another, I mean this is quite new, which is Caputo Fabrizio. So I mean in the a few years ago and 5 years ago. So, and Caputo and Fabrizio come out with the definitions because previously, so the kernel here have the singular kernel. And then so Caputo and Fabrizio try to suggest that, so we don't want to use a singular kernel, but we use this non-singular kernel. So they replace this singular kernel with this exponential negative alpha x minus t over 1 minus alpha. And then, so this is for when alpha is from 0 to 1. Then we can also extend it to alpha in the more general cases, so which is from alpha is more than 1. So it's basically it's about the same thing. So the only thing is you will see that this is up to, because we do until alpha 0.5, then this is the first derivative. Then if we do until alpha 2.5, so this is a higher order derivative. This is some of our publications regarding this Caputo Fabrizio operators. So in applied numerator mathematics and also in YD. So another type of the fractional derivative, if the operator here or the fractional derivative is regarding, say, this Artagana polynomial, which is they are using the mid-tet functions. So they are using these mid-tet functions instead of singular kernel. Okay. So there are a lot of interesting publications come out, but recently that a group of mathematicians is saying that so this is cannot be considered as the fractional derivative operator. So there are more. So regarding these definitions, so I just take few example. So perhaps that you can explore more regarding this one. So this is another one with Prabhaka fractional derivative. So I think it's the extension from the extension using these three parameters generalization of the mid-Taylor functions. So, and then we have this using these three parameter mid-Taylor functions. So we have this so-called the Prabhaka fractional integral, and also we have the so-called regularized Prabhaka fractional derivative. Here, I suggested some of the very good paper by a very well-known researcher. So actually, it's not limited to these three only, but I have a lot also. I just thought out due to the time limitation. So I just so three these three. So which is the maybe we can explore more regarding these few papers. Yeah, ladies and gentlemen. So let's talk about the problem for the fractional differential equation, fractional equation. So suppose that we are interested to solve whether a system or single fractional differential equations. So whether it's a linear or non-linear. So suppose that we can have this one. Okay, so the fractional derivative, so alpha 1. So say, for example, we define that the fractional derivative in the sense of capital. And then, so we have some initial conditions. We have some initial condition. So, so there are various type of the problems in the fractional calculus, which is the easier one is the fractional ordinary differential equations, and then fractional partial differential equations, and then we have these fractional integral differential equations. So why is the fractional integral differential equations? So basically, the fractional integral differential equations are the equations that have both derivative and also for the integral. And then we have some kernel function here. So this is something that we define as the fractional integral differential equation. So I believe that the next speaker will talk about more detail so regarding these fractional integral differential equations. So for this polynomial, so one of the methods that many people use or the easier methods that many people use to solve this fractional differential equation numerically is by using some of the polynomial. So I think this topic might be although a slightly old, but still new results and new to tackle the new problems is appearing every time. So like the polynomial, normally we can use the orthogonal polynomial. So this is a common one, and another one is not very common one is the non-orthogonal polynomial. And then for this orthogonal polynomial, so people might be using Jacobi polynomial, so which is including the Legendre, the Didin-Bauer, and Chebyshev, which is the domain is from the negative 1 to 1. And then if we want to have the domain from 0 to infinity, might be Raduri polynomial is more suitable, and we have the Hubbard polynomial, which is from negative infinity to infinity. And then here I give some tutorial regarding how we use this Legendre polynomial or the shifted Legendre polynomial to do the function approximations. Yeah, let me introduce to you that this Legendre polynomial. So the Legendre polynomial is defined in the negative 1 to 1, and then so you many way we have many way to get this Legendre polynomial. So one of the way is by using these recurrent regressions. Okay, which is when we have the lower order of the Legendre polynomial, then we can get the higher order of the Legendre polynomial. And then for the numerator purpose, numerator testing, so normally we interest to solve the problem so from 0 to 1. Then hence we need the shifted Legendre polynomial. So we can get the recurrent relation from here, or we can have analytical expressions for this shifted Legendrian polynomial. So this is the shifted Legendrian polynomial look like. And then say, for example, if we had a function y of x, then we are interested to express it in the shifted Legendrian polynomial. So that means we want to have this is a linear combination for this Cj, so Pj. So this Pj is supposed that is a shifted Legendrian polynomial. And then so we can write this function of y of x into these summation forms. And then because of the orthogonal polynomial, so we can get this Cj from the inner product straight away. And so the Cj is given by this one, so which is 2j plus 1, and then y of x, the pj, and the integrate from 0 to 1. But practically, we are not doing the summation up to m infinity. So we get approximate for all the functions up to the truncate at the m term, m plus 1 term. So suppose that we have a functions, then we approximate at this one Cj Pj from j from 0 to n. And then we want to get the C from, and then this C can be get from some inner product. And then also for this, the P, J, and then phi is given by this Pj. Then we can write also the first derivative for this Legendrian vector, Legendrian shifted vector of the shifted Legendrian polynomial. So in this using the metric form, so which is P1 Q phi of S. So we say that is the operation metric. Excuse me. Operation metric of derivative. We can get this operation matrix of derivative easily by using these expressions. If we want to get a fractional derivative for the any order for alpha, then we can also have the operation metric of fractional derivative, which is defined in a slightly more complicated term, but it's just a matrix. Then we can have this theta by using these expressions. So I give a simple example here. Then how we solve it by using this the operation matrix. Let's suppose that we have this province, the initial province, initial value province. We have the second derivative, and then this is the 1.5 order derivative, and then yf and gf. And then first of all, I purposely choose this example. Then I purposely choose this g of x is 1 plus x. But first of all, we try to approximate this 1 plus x by using shifted Legendrian polynomial. How's the thing look like? Okay, so g of x is 1 plus x. Okay, so say that this is the coefficients we are looking for. So g0 plus g1. So this is the because g0 actually is multiplied by 1. So this is the Legendrian shifted Legendrian polynomial, and then we have this order 1 shifted Legendrian polynomial 2x minus 1, and then this is the second order shifted Legendrian polynomial. And then this is the coefficients we are looking for. These coefficients we can get from the this coefficients we can get from using this the formula. Can get by using this formula. Okay, so it's not complicated, then we get this one. So that means we transform, we do the function approximation for 1 plus x. So and then we write down this 1 plus x in terms of shifted Legendre polynomial. So which is given by this one. And then we suppose that this is the solution y of x, so we want to find this one. And then we also approximate these solutions by using some shifted Legendre polynomial. Okay, so we have C0, P0 plus C1, P1 plus C2, P2. And then we want to approximate the derivative. So it's something like that. So this is the derivative, second derivative, d2. So we can consider that this operation matrix is replacing symbol by symbol. So this square derivative, second derivative, will be replaced by d2. So how we get this operation matrix D2? So we can get it from the D1. So D1 is the expression that I showed to you just now. So D1. So this is the D1. We can use in this one. And then after that, so then we take this, actually we take this, multiply this D1 with D1, then we will get this D2. So if we have the D3, then we can multiply D1 and D3 in order to get D3. And then for this D3 over 2, so we get from the operation matrix, this operation matrix, by using this term. So then we put all this D3 over 2, D2 into here. And then also for the y of x, we change it into the shifted Legendre polynomial form, and then also for the g of x, then we can get this. Okay. So then if we consider the initial conditions, so then we put x equal to 0, then we will get these expressions. So if we consider this first derivative, so we will have this. But then we get a system of linear equations. This is equation number 1, equation number 2, equation number 3. So if we have this system of linear equations, we can solve by using any method, then any appropriate method, then we get the answer for C0, C1, and C2. Sorry, there are a mistake here. I think this is C1. Okay. Then we get the answer for C1, C0, C1, C2, and then put into the y of x just now. Then we will get the solutions, the exact solutions. So for in this case, we will get because this is a very simple problem, then we can get exactly the exact solutions. So another type of the method that frequently being used here is wavelet. I think I may skip this one because due to the limit of time. So this is the wavelet. So this is another form of the wavelet. So I will rather focus on, please allow me to, because I think I have more about 10 minutes. So please allow me to go straight away to this our recent result here. So which is published in the European Physical Journal Plus. So where we are not using a polynomial to represent the solution for fractional logistic equation, but we are using just a number. Like here we call the modified Eulerian number. So where this Eulerian number is actually is the extent we get from the Poly logarithm. So this is the fractional logistic equations. So it's from the integer order logistic equations. So we have these problems here. And then if we have the beta is equal to 1, so it is actually this is the integer order logistic equations. And here we have the solutions. So the solutions is is given by this one. And then if we have the fractional derivative here, and then we do not have the exact solutions. So that is why these equations is one of the interest problems that the researchers in this field are looking for. So here we introduce this a number, so which is the modified Euclidean number. So if you are from the combinatory, maybe you can also explore this one. So like this is the Euler polynomial. So we get it from the get it from the Euler polynomial, and then we can get the polynomial also by using some generating functions. So this is a generative function that we can get Euler polynomial. And then this is the Eulerian polynomial. So again, this is the generating functions. And then from this generation function, if we expand it in the series forms, then we can get the Eulerian polynomial. And then, so if we use these fractional logistic equations, so this is fractional logistic equation. So the previous published result in 2018 is just assume that k is equal to 1. And then they solve it by using Euler method, Euler number. And then now we consider that this k is more general case, so which is not limited to 1, but is any positive number. And we let this 2k minus 1 is become equal to q. And then we introduce this q modified Eulerian number. So this is the generating functions. And then for these generative functions, we can get these q modified Eulerian numbers. So this is the q modified Eulerian number. It looks like this one from the previous generating functions. And then from here, so we can write down the solutions for these fractional logistic equations. So which is k is in more general terms, it's not only limited to 1, in terms of this cube modified Eulerian number. So that means we represent the solution by using using the cube modified Eulerian number. So when we have this one, and then we can get this the higher order of Eulerian number by using some lower order of Eulerian number. So given by these summations. The proof for this one is rather slightly tedious. So basically, so what we are going to do here is we excuse me. Sorry. Okay, so basically what we are doing here is we try to compare the left-hand side and right-hand side. And then we get this comparing the left-hand side and right-hand side. And then we get the terms. Then we compare that. Then we see that we can write down the higher order of Eulerian numbers, modified Eulerian numbers, in some expressions from the lower order modified modified Eulerian number. So this is some of the proving. So you may refer to our papers. So then after comparing the equating equating coefficient for the left-hand side and right-hand side, so eventually we reach to these expressions. So why we can express this modified Euler-Lien number so as the solution for these fractional logistic equations by using this equation 43. And then if we test for some example beta equal to 0.5 and beta 0.9, so we will see that if the power, the t power is being bigger and bigger, then actually the coefficient is getting smaller and smaller. And then we say that this is the numerical convergence. Not only this one, I think my student also doing this experiment. So actually, because the logistic equations, they actually they are doing this microalga algae, so drop in 20 days. And then actually this data is already we are using this some statistic method to throw away the outliers, and then here we get a very smooth result. So, but due to some limitations, so we only managed to get to 20 days the data. So I mean, obviously this is the logistic equation solutions. Um, then this is how we define some of the parameter. So we say that the x here is the biomass concentration of the microalgae, and then we have this xm is the maximum cell concentrations, and then t, of course t is represent time, and then this mu is represent the specific growth rate for this microalgae. And then we have, of course, then we have the subject to these non-negative initial conditions. Then so we put into this, we modify the logistic equation so into the ordinarily modified logistic equations. So, and then we introduce the fractional order. So this is the fractional order. Okay, and then on top of that, this fractional, so we define it in the capital sense. So this is the formula or the capital derivatives which I introduced to you before. And then we notice that, so if we are using the fractional order, so with difference order, a difference value of alpha, so we can get very closely to this then the data that we get from the experiment. So that's why this is just a starting research or this some starting study. So we try to relate it to the experiment data. So I believe that there are many ways, there are many other applications that we can explore. So in order to use the fractional derivative in the real life problems. I think that's all for my presentation. So hopefully you understand my English, and I think thank you for your attention.
Thank you, sir. Actually, some queries in the chat box of YouTube. Can I ask, sir, behalf of them?
Oh, can I see the chat box? I didn't see anything here.
I will ask this question, sir. No worries. Sir, what is the research area? Could you suggest some research areas that should be usable for in terms of fractional analysis? Some topics.
Some topic.
Yeah.
Oh, I think I thought in my slide allow me to represent against my slide. So mm, I think so. This is the I mean It depends on where your existing research in. So if you are from the peer match, then I think so many of the researchers in this field study the existence in uniqueness because it's very important. So the fractional differentiation in different destinations. So first of all, we might have the solution is exist and also for the units. So this is a very, I think, it's a very hot topic. And then also for the numerator, so or semi-analytical. So, but I will suggest that to more to focus on the fractional partial differential equations. There are a lot of problems. So might be people study now is regarding the two-dimensional. And then the recent topic is more to not only the fractional order, but it's the variable order. It's more general terms. And then, like if you are working in the applications, then yeah. So apply maths, then you can take. Say for example, you are study predator prey, then you can just extend it to the fractional predator prey model. So if you are study about, say for example, if you are doing optimal control, then you can extend it to the fractional optimal control. So anything we have the um, differential equation, so we can extend it to the fractional form. So hopefully I answer your questions.
Yes, sir. So actually, one more doubt is there. Actually, could you explain some of your what is your research area and what is the finding you made? That is, Dr. Chandrika from Telangana asked for you.
So you mean my sorry? Hopefully I understand the question. So I mean my
Research
research
topic.
topic. Um, so I mean this is some I told to you that some of my publications. So maybe this is regarding the fractional logistic equations. So by using just a number, so this is not very common, to be honest. So people are using mostly for the polynomial or vector. This is just by luck. So we managed to get just a number, and then also for partial differential equations. And then also this is another thing is not very common, so which is the right side. We are solving the right side capital fractional derivative. As I mentioned in the one of the slide before that, so the common one is we are using the left side. We are solving the left side left side capital fractional differential equation problem. But the right side here is not many people are concentrate about that one.
Okay.
And then also for capital Farizio, but I do not really recommend to trying to do something capital Farizio and Atagana Balenio because there are a lot of controversy regarding these two operators. And then this is a common one, so which is I think I write some together with my students. So all of the co-author is my student. Okay. So I'm using this semi-orthogonal polynomial. So this is not very common one, but people start using this genotype polynomial to solve more complicated problem.
Okay. Thank you,
Yeah.
sir. Actually, one more doubt from there.
Why I
Mrs.
cannot see the question?
Okay,
Sorry.
sir. One more doubt is there. Is the fractional analysis topic some research guide will be available in India also? Could you know
Sorry.
any other research in? Could you know any other research center for the same in India also?
Sorry. Can you repeat the question?
Sir, do the fractional research center
Mm.
what is the center is in India also?
Oh yes. Oh, I never get to know. So in which university?
Sir, actually, in India, any university is providing this because this is a new topic for us, and this one will be a new topic for all of them. That's why they are asking.
Oh no, I do not have much idea regarding that one. But actually, there are a lot of mathematicians in India are doing the research in fractional calculus. There are quite many. There are because I always see that uh, uh, mathematicians in in India come out with a very good method or come out with very good application regarding this fractional calculus.
Okay.
Yeah.
Thank you, sir. That is that much of courage. If anything is there, we will let you know, sir.
Okay, yeah. Thank you, thank you.
Yeah.
So
Thank you.
thank you,
Uh,
and hopefully you can understand my English, and then yeah, hopefully then you can learn something. Okay. Thank you, thank you.
Thank you,
Okay,
sir. It's a
so
wonderful section actually, because we know that you have a very busy person. In the busy schedule, you will make a time for us, and that's the
no, no,
first
no,
time
no.
I am
It's
making. I am
actually it's my
thank.
honor to present to you to all of you.
Actually, thank you so much, sir.
Thank
And
you, thank
you
you, thank
actually
you,
there are
thank you.
lot of comments is coming about your session is informative, and I will send you the chat box description to you, sir. Actually,
Mhm.
this will be a wonderful session we have with you, and thank you so much for your time and effort and for your detailed description, sir. Thank you, sir. We will look after
Thank
it
you,
for
thank you.
you in another session. Thank you so
Thank
much.
you for Mathematics Department of PRDS to giving me this chance to talk to all of you. Thank you.
Okay, dear participants, the feedback form is posted in the description box and also in the comment section. There will be no feedback will be not posted in groups, so please fill it. Thank you for the participation. Thank you, everyone.